Heidi-ho, Renaissanceteers, and welcome to the solution to Renaissance puzzle number 100. This is actually a 2-for-1 presentation. We'll show the solution to puzzle 100, and then we'll present the new puzzle 101. So sit back, relax, and enjoy.
Problem 100 referenced the Wikipedia page on gravity of Earth, which stated that you weigh less at the equator than at the poles because the oblate shape of the Earth puts you further away from the center of gravity at the equator. You were asked to test this claim by analyzing a simple model of an oblate planet comprised of 7 spheres to determine if you would weigh more on top of the center sphere or on the outside of one of the peripheral spheres. In this presentation, we will refer to Newton's law of universal gravitation, shown here, where m1 is the mass of the planet model, m2 is the mass of Pegman, and g is the gravitational constant, equal to approximately 6.673 times 10 to the minus 11th meters cubed per kilogram second squared. But g is a cumbersome number to work with, and since we are not interested in the actual gravitational values, but rather in relative values, let's define a simple unit to work with. And so I propose that Pegman standing on a sphere of radius 1 and mass m equal to 1 feels 1 gravitational unit for planetary planning. Yahoo! Also known as 1 guppy. And so for the purposes of this presentation, all gravitational values will be in guppies, unless otherwise specified. Jim Kirk did an ice analysis and report, which showed that you would weigh about 5% more on top of the center sphere than you would on a peripheral sphere. I won't show the math here. You can read it in Jim's gravity report. I have to admit that I thought Pegman would weigh more on the periphery, and had done a calculation some months ago that showed this to be the case. Unfortunately, that calculation was in error. And so, alas, there is egg on my face. This is more embarrassing than my treatise on cold fusion. Nevertheless, I am sticking to my guns. I still maintain that the Wikipedia statement is not quite right. I mean, look at the 7-ball model. On the equator, you are 3 times as far away from the center of gravity as you are at the pole. Gravity is inversely proportional to the distance squared. Shouldn't you weigh 9 times less at the equator instead of a measly 5% less? Furthermore, consider this. For the puzzle presentation, we showed the Earth as more oblate than it really is, to better illustrate the point. Let's take the exaggeration even further until the extremely oblate Earth takes on a shape like that of a vinyl long-playing record. There is little difference between standing on the center of this flat Earth and standing inside the center. And as you recall, when Pegman was inside the center of the Earth, he was weightless. So it would seem that the more oblate the Earth becomes, the less you would weigh when standing at the pole. And one last argument. Imagine that we remold all 7 balls of the cluster into 1 large ball of the same density. The new sphere would have mass equal 7, radius equal 1.913, which is the cube root of 7, and Pegman standing on the surface would feel a gravity of 7 divided by r squared, which works out to be 1.913 guppies. Jim Kirk showed that for the 7-ball cluster, gravity at the pole is about 1.536 guppies. So the gravity on the surface of the large sphere is about 25% greater than the gravity at the north pole of the 7-ball cluster, even though you are nearly twice as far away from the center of gravity. This demonstrates that the Wikipedia claim that being closer to the center of gravity means more gravity just ain't so. So we cannot completely discount the Wikipedia claim that the oblate shape of the Earth causes a decrease in gravity at the equator, but it seems clear that it cannot account for all of it. There is something more to the equation than simply the distance from the center of the Earth, something that has not been mentioned yet. And rather than just state what that something is, we shall now introduce Renaissance puzzle number 101, which will lead you to discover what that mysterious something is. In Doug Adams' novel, The Hitchhiker's Guide to the Galaxy, the Earth was destroyed by Vogons to make way for a hyperspatial express route. Let's imagine that in a parallel universe, the Vogons decide instead to make Earth a rest stop on the hyperspatial highway, and to eliminate annoying bumps on Earth's surface, such as Mount Everest and the like, they decide to pave over the entire planet with a layer of concrete. For this puzzle, let's ignore the oblate nature of the Earth and consider it to be a perfect sphere of radius 6,371 kilometers. And let's move Pegman out of the way so that he does not get buried in concrete. Here comes the Vogon Construction Company spaceship pouring its load of concrete, and it pours a layer 30 kilometers deep. And now Earth has a new radius of 6,401 kilometers. The question is, does Pegman weigh more on the original Earth or on the paved Earth? The paved Earth is more massive, but Pegman is further away from the center of gravity. So which wins out? To solve this puzzle, you will need to know that the mass of the Earth is 5.9 times 10 to the 24th kilograms. The density of concrete is 2,400 kilograms per meter cubed, and you'll need to know the gravitational constant. And this time we will find the true gravity, not Guppy's.
And so, Renaissanceteers, I hope you enjoyed this little presentation, and I hope you learned something as well, even if it was only to question everything you read, regardless of whether it comes from an authoritative source like Wikipedia or not. And as always, keep on Renaissancing.